Hello and welcome to lecture number 12. Continuing with our discussion on operators, let's look at two more operators, the throughout and the within. So throughout, as the name suggests, T throughout sequence 1, T is a signal, and I'll soon show you more on that. So T throughout sequence matches along a finite interval of consecutive clock ticks, as in here. So T must remain true throughout sequence 1, provided sequence 1 matches along that interval and T evaluates true at each clock tick of that interval. This is the interval we are talking about. So what we are saying that T must remain true throughout sequence 1. Now T can be an expression or a signal, but it cannot be another sequence. We'll look at within and we'll see that that problem will be solved there. And as you can see, T must remain true and sequence also must match during the time interval when T is expected to match. So T must remain true throughout sequence 1, provided that the sequence 1 also matches along the interval, which makes sense. Otherwise, why should T remain true if sequence 1 is not remaining true? And then once it is true throughout a sequence 1, then the property will pass. Okay, the best way to explain throughout is to take an application. So let's take this application. This is the spec, which says that when burst mode is asserted, output enable and data ACK must be asserted. And these are active low signal because of the underscore. So that means they must remain low. They must be asserted. They should go low within 2 clocks. And then output enable and DAC must remain asserted for minimum 4 clocks. So after the burst mode is asserted, which makes sense, output enable and data ACK must be asserted in 2 clocks. And then once they are asserted, they must remain asserted for minimum of 4 clocks. And burst mode must remain asserted throughout the duration of output enable and DAC, which is a very standard spec. When you want to do burst mode operation, burst mode goes high, output enable and DAC goes low, which basically means that output is enabled to transfer data. And let's say the burst mode is of 4, then output enable and DAC will remain low for 4 clocks, sending 4 data transfers. And burst mode cannot go high when these data are being transferred. So let's see how would we write such an assertion. First of all, like I've said many times before, think of an antecedent. If you look at this carefully, everything seems to start when B mode is asserted, meaning when it goes low. So I will start with $fell B mode as my antecedent. Now I have said before that here there are 3 different components of the spec. The best way to write an assertion is not write the entire assertion right here. Just break down each of the spec components into smaller sequences. So let's see how we do that. So what I've done first is one part of the spec says that output enable and DAC must remain asserted for minimum 4 clocks consecutively. So instead of looking at the rest of the spec, I said, okay, I must have a sequence that does this, because if this sequence fails, the whole property is going to fail. So what I did was sequence, I call it data transfer, and these output enable and DAC must be asserted within 2 clocks. So I'm waiting for 2 clocks, and then I'm looking to see if DAC is asserted and output enable is asserted, goes low, and that this entire Boolean logical AND remains asserted for 4 clocks. That's it. I'm not looking at throughout. I'm not looking at anything else right now. So I have broken down and taken one part of the spec and modeled it as you see here. Now, I'm going to tie things together. What we are asking is that burst mode must remain asserted throughout the duration of this OE and DAC assertion. The OE and DAC assertion is captured in this sequence data transfer. So now all I have to do is, after the B mode goes low, I go to the sequence check B mode. And the check B mode says that B mode, once it falls, must remain low throughout data transfer. And data transfer is what I just described. So as you can see, once you break down the sequences, it is much more easier to model complex assertions. So let's see how the whole thing works. Once the B mode goes low, this is where we start the whole assertion or the entire process, so to say. Once it is asserted, we then wait for 2 clocks, maximum 2 clocks, and then we see that both output enable and DAC are asserted, which is, as you can see here, first output enable goes low, and then DAC goes low. So basically, by the end of second clock, both pound to both DAC and output enable are asserted. And then we make sure with the *4 that they remain asserted for 1 clock, 2 clocks, 3 clocks, and 4 clocks. And then we make sure that burst mode remains low. It had gone low here throughout data transfer. So this 1, 2, 3, 4 are the 4 data transfers. And as you can see, burst mode was low, doesn't matter. But during the data transfer 1, 2, 3, and 4, it remains low. Once the data transfer is over, output enable will go high, DAC will go high, and so will B mode. This property can also be made a lot more complicated. For example, we can say that after 4 data transfers are complete, DAC must go high the next clock, OE must go high the next clock, and B mode goes high the next clock. I have removed some of the complexity, but in typical spec, you may see those requirements as well. So you can clearly see how throughout can be very successfully used in many timing diagrams or AC specs as the one that I've just shown here. Okay, let's look at the next operator, within. If you notice in the throughout, here, this was a signal or an expression. It could not have been a sequence. But the within is different from throughout, but both of the sequences are allowed. One within and one the larger one. One needs to be contained within the other one, and both of them can be sequences. So it matches along a finite interval of consecutive clock ticks, provided the sequence 2 matches. Here is the sequence 2 matches along the interval, and sequence 1 matches along some sub-interval of consecutive clock ticks. So here again, both are sequences and one is contained within the other. The start point of, when we say in sub-sum interval, the start point of the match of sequence 1 must be no earlier. Obviously, we are trying to see if sequence 1 is within sequence 2. And similarly, the endpoint cannot be later than the endpoint of sequence 2. Again, intuitively that makes sense. If sequence 1 is within sequence 2, then when the sequence 2 ends, the property will pass. Not when the sequence 1 ends, when the sequence 2 ends, because we need to make sure that sequence 2 is longer on both sides than the sequence 1. Again, let's look at a similar example, but with different specs. Again, let's say assertion of burst mode requires that master transaction and target X cycles follow the protocol below. Okay, after the burst mode assertion. So master transaction dictates that MTRX must assert the clock after B mode and remain asserted for 9 clocks. Okay, master transaction must remain asserted for 9 clocks. Now, target acknowledgement for the master transaction, it must remain asserted for 7 clocks within the master transaction MTRX. Okay, that is a spec. Let's see how we would model this. Again, I'm going to break it down. Okay, so TAC, target ACK, I'm going to take this part and model it. Target ACK must remain asserted for 7 clocks. That's it. That's all I care for in this sequence, because if this particular spec is violated, then the whole property will fail regardless of the relationship with within. So I'm going to say that whenever TAC falls, it must, starting that clock, pound 0, it must remain asserted for 7 clocks. That's it. I don't care for the rest of the spec right now. I'm just taking care of one part of the spec. The second thing I look at is that MTRX must remain asserted for 9 clocks. That's my other condition. So I have to make sure TAC remains asserted for 7 clocks, MTRX remains asserted for 9 clocks. So all I'm doing here is MTRX, once it falls, starting the same clock, it remains asserted or remains low for 9 clocks. So I'm still not worried about the within part. So now I'm going to tie the two together. Again, the antecedent, everything seems to start once the burst mode goes low. So that's my antecedent. Now what I'm going to do is, as this thing requires that TAC must be true, quote unquote, within MTRX. So I'm going to take the TAC relationship that I established here, and then I'm going to say that TAC must remain true within master transaction. So as you can see, you break it down, then you tie them together with a intelligent, as I call it, antecedent. Here's how the whole thing works. This is your AC specs, $FLB mode. Then there is the non-overlapping operator. Then basically MTRX falls. MTRX falls and it remains asserted for 9 clocks. We have to make sure, and that is made sure by this sequence here. Then TAC falls and TX remains asserted for 7 clocks. That is made sure by this sequence stack. And then the stack within SMTRX is here. The TAC remains low for 7 clocks. Master transaction MTRX is low for 9 clocks. And as you can see, here both are signals, but one can be a sequence. Actually, both are sequences. Sorry about that. So one sequence, TAC, remains or is true within the largest sequence, SMTRX. So TAC is a signal name, and STAC is what I call sequence for TAC, and this is the sequence for MTRX. So you can clearly see that the AC spec looks pretty complicated. But if you break it down and if you use operators such as throughout or within, then it's much more convenient and much more actually readable to write the assertion. Okay, I'm going to stop this lecture right here, throughout and within, which are very useful operators. Thank you for attending the lecture, and I'll see you soon in the next lecture.